In this video, we're going to show you how to balance oxidation-reduction reactions. If you take a look at this chemical reaction, you should notice that it's not balanced. We have 2 chromium atoms on the reactant side, 1 chromium atom on the product side, 7 oxygen atoms on the reactant side, and 3 oxygen atoms on the product side. So the atoms are not balanced. You also should notice that the charges are not balanced. The total charge on the reactant side and the total charge on the product side should be equal. On the reactant side, we have a -1 charge on this ion, a -2 on this ion. So the net or total charge on our reactant side is a -3. On the product side, we have a +3 here, a -1 here. So the net or total charge on the product side is a +2. So the charges are not equal. And that's what we have to do when we balance an oxidation reduction reaction, is not just balance the masses or the atoms, but we also have to be sure that the charges on the reactant and product side are equal. So that's what makes these types of reactions unique from just balancing a typical chemical reaction. So to balance an oxidation reduction reaction, we have to follow these steps very carefully. First step is easy enough. We can write the unbalanced net ionic equation, and that would be given to you in the problem. The second step, we have to decide which atom is being oxidized and which atoms are being reduced. When we do that, then we divide our chemical reaction into 2 half reactions. One half reaction which has the species that are being oxidized, the other half reaction which contains the species that are being reduced. Then what we'll do is we'll balance those 2 half reactions separately for atoms and charges, and once we get them both balanced, then we add them back together again. So in step 3, we balance each half reaction for all of our atoms except for oxygen and hydrogen. And we do that by adding coefficients to either side, the reactant or product or both. Step 4, we balance our oxygens and hydrogens. We balance oxygens not by adding oxygen, but we add water to the side that needs oxygens. If we need to balance the hydrogens, we add an H+, one or more H pluses to the side that needs hydrogens. So once we have the atoms all balanced, then we move to step 5 where we balance the charges. For each of our half reactions, we look at the charge on the reactant and product side, and we see which side, the reactant or product side, is more positive, and we add enough electrons to that side in order to balance the total charge on the reactant and product side. And we do that for both half reactions. So one half reaction, we should have one side gaining electrons. In the other half reaction, one side should be losing electrons. And we have to be sure that the number of electrons being lost in one half reaction is equal to the number of electrons being gained in the other half reaction. Occasionally what we have to do is multiply one or both of the half reactions by some coefficient in order to get the number of electrons to be equal. So we'll show you how to do that in just a minute. Once we have the charges balanced, then we move to step 6. We add the 2 half reactions together to get an overall balanced equation. And occasionally we can cancel some species on the reactant and product side that are the same. Then we can check our answer to be sure that everything is balanced, both the masses and the charges. So let's look back at our equation that we looked at just a minute ago. And let's use this as an example to show you how to balance an oxidation reduction reaction. So you notice one other thing, that this says that this occurs in an acidic solution. We'll show you why that's important in just a little bit. But our first step told us to write the net ionic equation, so we've done that. The second step, decide which atom is being oxidized and reduced, and then split our chemical equation into two half reactions. So pause this video for just a minute and see if you can do that. Okay. So to determine which side is being oxidized or which atom is being oxidized, which is being reduced, we have to assign oxidation numbers. Our oxygen is -2 on the reactant side and the product side, so the oxygen atoms are neither being oxidized nor reduced. If we look at the oxidation number of our iodine, on the reactant side it's a -1. On the product side we have a +5. Therefore, the iodine is losing electrons. Since its oxidation number is becoming more positive, it's losing electrons. So we say the iodine is being oxidized. Our chromium, it has an oxidation number, each chromium of +6 on the reactant side. On the product side, each chromium has a +3. Therefore, our chromium, its oxidation number is decreasing, and so it's gaining electrons. So the chromium is being reduced in this reaction. So let's divide this into our two half reactions. The chromium is involved in the reduction half reaction, so this would be our reduction half reaction. The iodine is being oxidized, and so this would be our oxidation half reaction. So we split the reaction into two half reactions. Now you notice that there are oxygens on this side but none over here. And same thing here, we have oxygens here but none over here, but that's okay, we'll balance those in just a minute. Step 3 says balance the half reactions for all atoms except for oxygen and hydrogen. Okay, pause this for just a minute and balance that. Okay, so to balance the half reactions for everything except oxygen and hydrogen, we notice that we have two chromiums here, so we need to put a coefficient of 2 here to balance our chromiums. In this half reaction, our iodine, we have 1 here and 1 here. So our iodines are already balanced. We don't have to add anything. So let's move on to step 4. Step 4 says balance each half reaction for oxygens and hydrogens. We add water to the side that needs oxygen and hydrogen in the form of H+ to the side that needs hydrogens. So again, pause this, take a minute, and see if you can balance it. Okay. So I noticed that in the first half reaction, I have 7 oxygens over here and none here. So I need to add oxygens to the product side. To add oxygens, I add them in the form of water. So I need 7 oxygens, so I add 7 waters on this side. Okay. Now my oxygens and my chromiums are balanced, but I have now 14 hydrogens, so I need to add 14 H+, because again we add hydrogens in the form of H+, or hydrogen ions, to the reactant side. So now I have 14 H+, or 14 hydrogens, over here 14 hydrogens, 2 chromiums, 7 oxygens, 7 oxygens. So all of my masses are balanced in this half reaction. In this half reaction, I have 3 oxygens here, so I need to add 3 waters over here. So now I have 3 oxygens. That gives me 6 hydrogens on the reactant side. So over here, to balance that out, I need to add 6 H+. So now I have 6 hydrogens, 3 oxygens, and 1 iodine, and 1 iodine. So all of my masses are balanced in both of my half reactions. Now, step 5, we need to balance the charges by adding electrons to the more positive side. So pause this for a minute and see if you can balance the charges. So if I look at this half reaction, I see that I have a +1 here, and I have 14 of those. So I have a total of +14 and then a -2 from the dichromate ion. So +14 and a -2 give me a total of a plus 12 on this reactant side. On this side, I have a plus 3, and I have 2 of those chromiums, so I have a total of plus 6. The water is electrically neutral, so it doesn't have any charges. So we said over here we have a plus 12 on the reactant side and a plus 6 on the product side. So I need to get those charges to be equal, not necessarily 0, but just equal. So in order to get the charges equal, I add electrons to the more positive side. If I add 6 electrons to this side, then I have a total of, I had plus 12 and a minus 6, because electrons have a negative charge. So plus 12 and minus 6, that gives me a total of a plus 6 on this reactant side. So my net charge now is a plus 6 on the reactant side and a plus 6 over here. So now this half reaction is balanced electrically. If I look at this oxidation half reaction for the second one, I notice that on the reactant side I have a minus 1 charge. My oxygen is neutral, so I have a total of minus 1 over here. On the product side, I have a minus 1 charge from this ion. I have a plus 1 here, but again, I have 6 of these, so I have to take into account the stoichiometry. So I have a plus 6 and a minus 1. And so my total net charge over here is going to be a plus 5. So a minus 1 on the reactant side and a plus 5 on the product side. So I need to add electrons to the more positive side, that would be the product side, and I need to add enough electrons to get this side to have a net of a negative 1 charge. So it'll be equal to the charge over on the reactant side. So in order to get from a plus 5 to a minus 1, I need to add 6 electrons here. So now this side has a minus 1, this side has a minus 1 plus 6, so a total of a plus 5, and I added 6 negative charges, 6 E minus, and so now this product side has a negative 1 charge. So my half reaction, my oxidation half reaction, is balanced electrically. Now you notice that here we have 6 electrons, here we have 6 electrons. They're the same. This half reaction is gaining 6 electrons. This half reaction is losing 6 electrons. And you must always have the same number of electrons being lost as gained. In this case, they're both 6, but sometimes they may not come out to be the same, and you may have to multiply by some coefficient. We'll practice one where that is the case a little later. So I don't need to multiply either of these by any coefficient. So let's move on to our next step. Okay. Step 6 says to add the 2 balanced half reactions together, cancel the electrons and any other species that appear on both sides of the equation. So if I add them together, I get 14 H pluses. I get my Cr2O7 2 minus, and then I get my 6 electrons, 3 waters, and 1 iodine. All of this will go on the reactant side. All of the species over here for these 2 half reactions will go on the product side. Now when I add them together, I notice that of course I'll have 6 electrons on the reactant side and 6 electrons on the product side. Those electrons should always cancel. I also see that I have 6 hydrogen ions on the product side over here, and I have 14 over here. These 6 hydrogen ions will cancel with some of these. They'll cancel with 6 of these, leaving me 8 H pluses remaining. So I can cancel my electrons. I can also cancel my H pluses. I've got water on this side and water over here. I have 3 waters. That'll cancel with 3 of these waters, leaving me 4 waters. But those are the only species that'll cancel. So I end up with 8 hydrogen ions plus my I minus, my Cr2O7 on the reactant side. On the product side, I end up with my IO3 minus ion, 2 chromium ions, and 4 waters, because we canceled 3 waters, so we still have 4 remaining. So this is my overall balanced equation. The final thing is we want to just check to be sure that this final equation is balanced for both charges and for the masses. So I have 8 H pluses here, or 8 hydrogens. On the product side, I have 4 times 2 is 8 hydrogens. I have 1 iodine, so that's balanced. I have 2 chromiums, I have 7 oxygens. Here I have 3 and 4, 7 oxygens. So all of my masses are balanced. My charges should also be balanced. I have 8 plus charges, a -1 charge and a -2, so that 8 minus 1 is 7, -2, that gives me a total of a +5 on my reactant side. On my product side, I have a -1, a +3, but I have 2 of those, so a total of +6, -1, and the oxygen is 0, so my net charge on the product side is also a +5. So this reaction, I know I've gotten it correct because my charges are balanced and my masses are balanced. Now, one other thing, you notice at the beginning we said that this reaction occurred in acidic solution. We have some H plus ions in our balanced equation, and since this is an acidic solution, that's allowed. Now, if this was a basic solution, if this was an oxidation reduction that occurred in a basic solution, and we would be told that in the question, we could not have the H plus ions. We'd have to do one more step to get rid of those. But for this, because it occurs in an acidic solution, this is our final answer. Okay, let's try one more problem, balancing an oxidation reduction reaction. And this is a reaction that occurs in basic solution. So we'll show you it balances just like the one that we saw before in acidic solution, but we do have to sometimes do one extra step at the very end. So we'll look at that. So if we look here, we see that this equation is not balanced. Over here I can see that I have 4 oxygen atoms on the reactant side. On the product side I have 5, so it's not balanced. I also have a -1 and a -1, so a total of -2 charge on the reactant side and a -1 charge here. So this equation is balanced, is not balanced for masses or for charges. So we have to go through our steps again and balance this. So the first step was to write our net ionic equation that's provided in the question. Second step, we have to decide what's being oxidized and reduced and split it into our 2 half reactions. So pause this for a second and see if you can split this into its 2 half reactions. Okay. So to decide what is being oxidized and reduced, we have to assign our oxidation numbers. Our oxygen is a -2 over here, a -2 there. So the oxygen is neither oxidized or reduced. Our manganese, its oxidation number is +7 as a reactant, +4 as a product. So since its oxidation number is becoming less positive, it's gaining electrons. So the manganese, we would say, is being reduced. The bromine on the reactant side is a -1. On the product side, it's a +5. Its oxidation number is becoming more positive, and so the bromine is losing electrons. So we'd say the bromine is being oxidized. So when we write our 2 half reactions, the bromine is going to be in our oxidation half, the manganese would be in our reduction half reaction. So we could split it into 2 half reactions, which would look like these. Step 3, we balance both half reactions for everything except oxygen and hydrogen. So if I look at the bromines, I have one bromine here, one bromine on the product side. That's balanced. The manganese in the other half reaction, we have one on the reactant side, one on the product side. So our manganese are also balanced. So that's already done. We don't have to add any coefficients. Step 4, we have to balance our oxygens and hydrogens. Remember to add oxygen in the form of water to the side that needs an oxygen, and we add hydrogen in the form of H+ to the side that needs hydrogens. So pause this video and see if you can balance the oxygens and hydrogens. So my bromine, or the bromine half reaction, on the product side we have 3 oxygens, so we need to add 3 waters to the reactant side in order to balance the oxygens. Now we have 6 hydrogens, so we need to add 6 H+ in order to balance those. So now we have 6 hydrogens, 3 oxygens, and 3 oxygens, and 1 bromine, and 1 bromine. So we have all of our atoms are balanced in that half reaction. In the second half reaction, we have 4 oxygens on the reactant side, 2 oxygens on the product side, so we need to add 2 waters to the side that needs our oxygens, the product side. Now we have 4 hydrogens, so we need to add 4 H+ in order to balance those. And that gives us a equation that's balanced for our hydrogens, manganese, and oxygens. And we can go on to step 5, where we need to determine which side is more positive for each half reaction and add enough electrons in order to get the reactant and product side to balance in charges. So pause the video for a minute and see if you can balance the charges for the 2 half reactions. Okay. So for my first half reaction, I have my water, which is electrically neutral. My bromine, I have a -1 charge, and I have 1 of those. So my reactant side, I have a total of a -1 charge. On the product side, I have a -1 here, and I have 6 + 1 charges. So the total charge on the product side is 6 and a -1, which gives me a total of a +5. So the product side is +5. The reactant side is -1. The product side is the more positive side, and so that's the side I add my electrons to. I need to get the charge on the product side to equal -1. So I would add 6 electrons to the product side. Now I have a total of -1 here and a -1 on the product side. For the other half reaction, I have 4+, I have a +1, I have 4 of those, and a -1 here. So I have a total of a +3 on my product side. Over here, this manganese is neutral, so 0 charge, and my water is neutral, so it's 0 charge. So I need to add electrons to the more positive side. That would be the reactant side, which we said had a net of a +3 charge. So I need to get the total charge on my reactant side to equal 0, because that's the charge on the product side. So I add 3 electrons in order to get the total charge on the reactant side to be equal to the total charge on the product side. So I add 3 electrons. Now if you notice, I have 6 electrons being lost in this half reaction and 3 electrons being gained in this half reaction. You always must have the same number of electrons that are being lost in one half reaction as is being gained in the other. So the number of electrons being transferred must always be the same. So I need to multiply this half reaction by some coefficient. Now sometimes you may need to multiply both, but in this one we could multiply the second half reaction by 2, and that would give us 6 electrons, which would equal the number of electrons being lost in our first half reaction. So I need to multiply this whole half reaction by 2 not just the electrons, but the whole half reaction by 2 in order to get those electrons to be the same. So that's going to give me 6 electrons, 8 hydrogen ions, 2 permanganate ions, 2 manganese dioxides over here, and 4 waters. So I have to multiply this whole half reaction by 2 so that the electrons will cancel. Next, once I have my charges balanced, I need to add the 2 half reactions together and cancel any species that will cancel. So pause this video for a second and see if you can add those together. So here you can see we've multiplied everything by 2, and so our electrons are the same. So our electrons in this half reaction and this half reaction will cancel, which should always be the case. Let's see if there's anything else that will cancel. Here we have 3 waters. Here we have 4 waters. So these 3 waters, pull up the pen here. So these 3 waters will cancel with 3 of these. Oops. And so I'll be left with 1 water on this side. Also, my hydrogens, I have 6 hydrogens here, H+ ions, and I have 8 here. So these 6 will cancel with 6 of these, and that will leave me 2 remaining. Now my bromines won't cancel, or my manganese won't cancel either. So those are the only species that will cancel. So then I need to add them all together. I end up with my 2 H+, my 2 MnO4-, my 1 Br-. On the product side over here, I have my 2 MnO2s, my 1 water remaining, and my BrO3- ion. And so finally, we need to just check this to be sure that it is indeed balanced for both atoms and charges. So let's check the atoms first. I have 2 hydrogens and 2 hydrogens. I have 2 manganese and 2 manganese. I have a total of 2 and 4, so I have a total of 8 oxygens. Over here I have 4 plus 1 plus 3, so I have 8 oxygens over here as well. I have 1 bromine atom and 1 bromine atom. So my masses are balanced, and then I need to check the total charge on each side. Here I have, don't forget your coefficients, I have a +1 and 2 of those, so I have a +2. Over here I have a -2, so those cancel to give me 0, and then a -1 here. So I have a total of a -1 charge on my reactant side, and then on my product side, this is 0, and this is -1. So that's balanced. So this equation is balanced for both masses and for charges. So if this were in an acidic solution, I would be done. That would be the correct answer. But I have to do one more step because the question told me that this reaction occurs in a basic solution. If you notice, we have H+ ions, which of course represent that this is an acidic solution. So you cannot have H+ ions in your final equation if it occurs in a basic solution. So we have to get rid of those. To do that, I would add hydroxide ions to the side that has the H+ ions. Put a pen here. So I need to cancel these 2 H+ ions. So I'm going to add, let me see if I can write this here. So I need to add 2 hydroxide ions to the reactant side. Now, whatever you add to one side, you have to add to the other. So over here, I have to add 2 hydroxide ions. Pardon my shaky writing here. Okay. So I add 2 hydroxides here. Now these hydroxide plus H pluses, of course, those combine together to give me two water molecules, H2Os. Okay. So to get rid of those H plus ions, I add two hydroxides. I also have to add those two hydroxides to the product side over here. Then I add these two together to give me two waters. Now finally, my two waters here, you can see here I've combined the two hydroxides to form my two waters. Here's my two hydroxides. This water will cancel with one of these waters, and I'll end up with just one water here. So my final equation here, let's just check to be sure it's balanced. I have a 1 oxygen, 8 oxygen, so I have a total of 9 oxygens here. I have 4 and 3 is 7, 8, 9 oxygens here. My hydrogens, I have 2. Over here I have 2 hydrogens, 2 manganese, 1 bromine, 1 bromine. So all of my masses are balanced. And then I finally just need to check to be sure my charges are balanced. I have a -1. I have 2 of those, so that's a total of a -2 and a -1. So that gives me a total of -3 on the reactant side. On the product side, I have a -1 and a -1. We have 2 of these, so a total of -3. So here we know we've got the correct answer because our masses and our charges are balanced. And since this occurs in a basic solution, we don't have any H pluses. We have hydroxides representing a basic solution. So this would be a correct balanced equation.